Today we're going to look at different types of convergence. So in other words, what do we mean by a sequence of random variables converging to another random variable? Now it turns out that there are two types of convergence which are most important. I'm going to start with convergence with probability 1. So in convergence with probability 1, the random variables themselves will converge to a number with probability 1. In other words, the probability that the limit as t goes to infinity, that x of t equals 1. To get a feel for what's going on with convergence with probability 1, let's look at an example. Suppose that I have independent, identically distributed Bernoulli random variables with parameter 1/2. So B1, B2, etc. are IID Bernoulli random variables with parameter 1/2. I'm going to use those random variables to form binary digits. So if the initial sequence was 0, 0, 1, 1, 0, 1, 0, and so on, my first number in my sequence would be 0 divided by 2. The second number in my sequence would be the first number plus 0 over 4. The third number would be the second number plus 1 over 8, and so on. In general, the nth number would be the sum, as I goes from 1 to n, of b sub I divided by 2 raised to the ith power. Now, if you take the limit of that, it's going to converge to a number. You can check by the ratio test that no matter what this sequence is here, this sum is going to converge to a single number. And it turns out it's not too hard to show that if x is the sum as I go from 1 to infinity of this b sub I over 2 sub I, that itself has a uniform distribution. Even though the bi's were discrete, the infinite sum is a continuous random variable, and it has a uniform distribution from 0 to 1. And this is a case where the x sub I, or the x sub n, always converge to x. There are no exceptions. There's no way it can fail to converge to x. And so in fact, the probability that the x sub n converge to x equals 1 in this case. Okay, so this kind of convergence is great. We have the x sub n maybe not always converging to x, but at least the set of outcomes where they don't converge to x has probability 0. But unfortunately, that doesn't cover all the cases we need. The second type of convergence that I want to talk about is convergence in probability. Those of you who've had some real analysis might know this as convergence in measure. It's the same idea. Now, convergence in probability, I'm going to start with an example before I get to the definition. Now, my example is going to be similar to the first one. I'm going to have C1, C2, etc., all Bernoulli random variables. But now, even though they're independent, I'm going to make them have different distributions. So all Bernoulli and independent. But I want the ith variable to be Bernoulli with parameter 1 over I. So just a reminder, what that means is that the probability that the CI equals 1 is 1 over I, and the probability that the CI equals 0 is 1 minus 1 over I. So because it's a Bernoulli random variable, it's either 0 or 1, and the parameter is telling you the probability that the random variable equals 1. Okay, so when we look at these random variables, the probability that they equal 1 is going down, strictly. In fact, as I goes to infinity, the probability that C1 equals 1 is going to 0. The probability that CI equals 0 is converging to 1. So this is another type of convergence, different from convergence with probability of 1, where in some sense the C sub I are converging to 0. They're just not converging with probability 1. So here's what I mean by that. In convergence with probability 1, we looked at the probability that the limit of the random variables and said that that was equal to 1. Now, for convergence in probability, if we look at the probability that the CI is different from 0, and we look at the limit as I goes to infinity, that's 0. So in other words, we have a situation where the chance that we make a mistake is going down to 0 as I goes to infinity. Another way, of course, to state this convergence with probability 1 is that the probability that the limit as t goes to infinity of x of t does not equal x equals 0. So we can put both of these sort of in the 0 framework rather than the 1 framework. Okay, now I claim that the CIs converge to 0 in probability, but what is the probability that CI converges to 0? So in other words, what I'm getting at is I told you two different ideas, convergence with probability 1 and convergence with probability, and I want to know, are they the same? And the thing is, the CI will converge to 0 in probability, but it turns out the probability that the CIs converge to 0 is 0. Here's why. So when I look at these random variables, C1, C2, C3, and so on, they're either 0 or 1. And the probability that they're 0 or 1 keeps going down. The first one has, well, probability 1 being 1, so that should have been 1. C2 has probability 1/2 of being 1. C3 has probability 1/3. C4 has probability 1/4, and so on. However, suppose that I cut it off after a particular point, C4, and ask, in this sequence out here, what's the chance that I have at least one more 1? And what's the chance that I have at least one more 0? Well, it turns out that the chance that I have at least one more 1 and that I have at least one more 0 are both going to be 1. These are both probability 1 of S. Why is that? Well, the probability that C sub n equals 1 for some n greater than 4 is the same as 1 minus the probability that C sub n equals 0 for all n greater than 4. Remember, when you negate a statement, you change for sums to for alls. And the probability that Cn equals 0 for all n greater than 4, well, the probability C5 equals 0 is 4/5. 4/5 is the probability that C5 equals 0. The probability that C6 equals 0, well, that's 5/6. Even closer to 1 than the probability that C5 equals 0. And that pattern continues. We then multiply by 6/7, by 7/8, by 8/9, and so on. And this forms what's called a telescoping product. 5's cancel, the 6 cancel, 7 cancels, the 8 cancels. And you can see, as we go farther out in this product, as we take the limit as the number of terms goes to infinity, I always thought before here that this number is getting bigger and bigger. So this limit is just equal to 1. And so the probability that there's at least one 1 for n greater than 4 is 1. And in fact, it's even more likely that there's a 0, because each individual CI has a greater chance of being 0 than it does of being 1. So that's also 1. So the probability that both of these events occur is also 1. Well, what do we call a sequence where no matter how far out in the sequence we go, we'll always find a 0? And no matter how far out in the sequence we go, we'll always find a 1 somewhere. Well, that just doesn't converge to anything. There's no way it can converge to 0. There's no way it can converge to 1. So Cn, I should say the limit as n goes to infinity of the Cn does not exist. There is no limit of the Cn as n goes to infinity. So there's no way we can talk about the Ci going to 0 with probability 1, because the C random variables don't converge to anything at all. So this convergence and probability notion allows us to deal with variables that may not converge on a sequence basis, but are in some sense getting closer or farther away from a particular number. In this case, the CIs are getting closer and closer to 0, because as we go out in the sequence, we're going to see more and more zeros, until mostly we have zeros in our sequence. So it's just there's no one way of describing convergence which is correct. It's just a different way of understanding what's happening in this sequence as the terms go to infinity. Okay, so with that in mind, I'm going to write a formal definition of convergence and probability. So convergence in probability, we say that x1, x2, x3 is converging to x in probability if for all epsilon greater than 0, there exists, if we look at the limit as t goes to infinity, of the probability that x of t is different from the thing that we think it's converging to by distance more than epsilon, if the limit of those sets of probabilities equals 0. So to answer the question of the day, we could mean one of two different things when we talk about convergence. We could mean that the probability that the limit of the sequence converging to x is equal to 1. And we could mean that for all epsilon greater than 0, the limit of the probabilities that our sequence is far away from the thing that we say that it's converging to, that goes to 0. Generally speaking, most people like this definition more than this definition. So it helps to have a picture to understand what's going on. So let me draw a picture. So remember, we use omega to mean sort of our set of all random things. And in this case, we've got omega here. And if we have convergence with probability 1, what's going on is that if I look at the set of possible random outcomes, at the set of little omega, such that as t goes to infinity, x of t is converging to our value x. So if I look at omega and omega prime, and of course there's an infinite number of possibilities where x of t could be converging to x. But there also could be some omega, maybe omega double prime, where as t goes to infinity, x of t doesn't converge to x. Maybe it converges to x plus 1. But if I look at all these possible outcomes where we fail to converge, the set of such omega has probability 0. So if I look at the set, at the probability of all omega, such that when I use that level of randomness, I don't converge to x, that's equal to 0. So maybe along this entire line, any omega on here, the x of t will not converge to x. But everywhere off of that line, with probability 1, I will get convergence to x. That is convergence with probability 1. What about convergence in probability? That also has a picture, but it's a little different. Now what I'm going to do is I'm going to think about x, and I'm going to picture picking some epsilon that tells us our tolerance for being away from x. So I want to know when is my outcome between epsilon, is between x plus epsilon and x minus epsilon. Well, a lot of omega. X of 1 is going to be within epsilon of x. But there might be some set of omega, let's call it A1, such that if I pick omega in A1, x1 is outside of this epsilon region around x. Now, on the other hand, by the time I get to x2 might be within this epsilon region of x. And of course, it's going to have a different set, A2. And this different set tells us the set of omega such that x2 fails to fall within epsilon of x. So now we can ask the question, well, what's happening to these sets? A1, A2, A3, maybe A4 is over here. What's happening to the size of these sets? And I claim that no matter how tight I make epsilon, no matter how close epsilon is to 0, the limit as t goes to infinity of the probability of these a sub t's equals 0. In other words, the set of a's, the size of the a's, as measured by probability, is getting smaller and smaller. The set of outcomes where we fail to land within epsilon of our true value is going to 0. So which is stronger? Which is stronger? This notion of probability with convergence 1 or this notion of convergence in probability? And it turns out that as long as you have convergence in probability with probability 1, you'll also have convergence in probability. So, fact, if the x of I, or x of t in this case, converge to x with probability 1, then they also converge in probability. So in that sense, convergence with probability 1 is a stronger condition than convergence in probability. If we have convergence with probability 1, we're guaranteed convergence in probability. But as we saw from our example, convergence in probability does not guarantee convergence with probability 1. So for that reason, we call convergence with probability 1 strong convergence. And we call convergence in probability weak convergence. If you've heard, of course, of the strong law of large numbers, that tells you that the probability that the sample average of IID, integrable random variables, converges to the true expectation is equal to 1. So strong convergence is convergence in probability 1, weak convergence is convergence in probability. Well, so why do we have weak convergence at all? Because unfortunately, it's only possible for some results to prove that weak convergence happens. The good news is that for weak convergence, we know how to exactly characterize when we can swap limits and expectations. That's a very nice thing. That characterization is called uniform convergence, and we'll talk about that a little later on in the course. Thanks for watching.